Hi, welcome to Chapter 4, Part 5, where we're going to talk about Section 4.6. This is the last video of Chapter 4. We're going to talk about solution stoichiometry and chemical analysis. So the topics that we're going to cover in this video are how to use molarity and stoichiometry to perform calculations, in particular neutralization calculations and precipitation calculations. What is a technique called titration? How do you perform titration and use the data you collected to do calculations? So here is a flowchart or schematic to show you how you could use molarities and stoichiometry to do calculations. So if you just kind of walk through it, if you have grams of A and you divide by the molar mass, you will end up with moles of A. And then if you know the volume in your solution, you can divide by the volume and you end up with molarity. But if you have moles of A right here, you could use your mole ratio from your balanced chemical reaction to get moles of B. And then you could go either way, go get grams of B, or if you know the volume, you could get molarity of B. So sometimes these flowcharts are good for your visual learners. If you're like, well, after seeing this, we're going to do a couple examples and hopefully that'll clear it up. So here's the first example of an acid-base reaction. So it's a neutralization reaction. So when solutions of hydrochloric acid and sodium hydroxide are mixed, they react according to the balanced equation up above. And they give you water and sodium chloride. If you have 10 milliliters of 2.0 molar NOH solution, how many milliliters of 1.5 HCl solution will you need to neutralize this reaction? Okay, so the first step we're going to do is take our molarity of sodium hydroxide and the volume that they give us to calculate how many moles we have. So remember, molarity, this capital M is molarity, or you could call it a molar, is moles per liter. So since it's 2 molar, it's 2.0 moles per liter of NaOH. And since this is liters and our volume that they give us is in milliliters, we need to convert it. So by multiplying it by 1 liter over milliliters, what happens to my liters? They go away, and now I have moles per milliliter. And they say you have 10 milliliters, so I can multiply it by milliliters, which will then cancel out the milliliters, and I end up with moles. So now that I have moles of sodium hydroxide, I can use the mole ratio to get moles of HCl. Now in this example, our mole ratio is 1 to 1, right? If there's nothing written in there, then it's a 1. So it's a little bit straightforward or easier because it's a 1 to 1 mole ratio. So here I have my moles of sodium hydroxide times my mole ratio. So because there are 1s in front of here, 1 mole of sodium hydroxide will neutralize 1 mole of HCl. So if I stopped right here, I will now have moles of HCl. Is that what it's asking us? No, it's asking us what volume, okay? But it's giving us the molarity. And remember, molarity is moles over liters. So since when I stop here, I have moles of HCl, I need to put moles of HCl on the bottom so that they will cancel out. So remember your dimensional analysis. You always want to check your units to see that they're canceling out. Remember, 1.5 molar is moles over liters. So when I just do 1 over that, the liters go on top and the moles are on the bottom. But it's asking milliliters, so I need to now get rid of my liters and use the conversion between liters and milliliters, and I end up with 13 milliliters of 1.5 molar HCl. Now there is an easier way to do this, which you probably learned in honors chem towards the end of the year, where you could use this equation right here. Na, Va, Ma, Nb, Vb, Mb. So the A's are for acid. A stands for acid, and the B stands for the base. This N number here and here is the number of for the acid, you have to look at the formula of the acid. It's how many hydrogens are in your acid. So at HCl, because our acid is HCl, Na is equal to 1 because there's one H. And our base is NaOH. So Nb is how many OHs there are, and there's only one in there. Va is the volume of the acid, which is what we are looking for. So you put a question mark. Ma is the molarity of the acid, which they give us is 1.5. Vb is the volume of the base, and Mb is its molarity. Okay, so now you could plug it into the equation. So you have your 1 for Na, Va is what we're solving for, 1.5 is the concentration, and then you do the same thing for the base, and then you solve for Va and you get the same answer. So this is a easier way, but it is also important to understand the stoichiometry and where it comes from. So here's an example for a precipitation reaction. It says how many liters of 0.5 molar HCl are required to react completely with 0.1 moles of lead 2 nitrate, forming a precipitate of lead 2 chloride. So the first thing you want to do is write the reaction and balance it. Now you see in this case, we had to put some 2's in there to balance it. Now let's start with our given. We are given 0.1 moles of lead nitrate. So we're going to use this 0.1 moles of lead nitrate and the mole ratio to figure out how many moles of hydrochloric acid we need. So here I start with my 0.1 moles of lead nitrate, and because lead nitrate is the unit of my given, it goes on the bottom so they could cancel each other out. My mole ratio comes from my balanced equation. This 2 here is where we got the 2, and since there's nothing written here, that is a 1. So if I stopped here, I would have moles of hydrochloric acid, but I don't want moles, I want to know liters. So now the molarity of my hydrochloric acid comes in here, and remember, molarity is moles over liters, right? So if I do 1 over the molarity, my units flip-flop, so I end up with liters on top and moles on the bottom. Why did I do that? Because I am ending with moles of hydrochloric acid, and I need to cancel that out, and I'm looking for liters of HCl. So once I do all that, I get that I need 0.400 liters of 0.5 molar HCl. And why did I write all these zeros here? Well, if we're using sig figs, this has 3 sig figs, and our answer should have 3 sig figs. Now, how do we come about knowing the volume and the concentration of what we're mixing? Well, we have to do something called a titration experiment. And when you do titration, it's an analytical technique in which you can calculate the concentrations of a solute in a solution. So if you're given an unknown solution and you don't know its concentration, you would have to titrate it to figure out what the concentration of that solution is. And I have shown here 4 video clips that I would like you to go watch that go over how to perform a titration experiment. This first one here is pretty good. It shows you a lot of good details. And then this Isaac Teach goes a little bit more into it. And then the B part is how to do calculations. And this last one kind of gives you overall how to do the experiment and calculations. So please watch those 4 videos. And I'm going to just kind of summarize here what is in the picture. So here you have an Erlenmeyer flask. And you have to rinse that with distilled water before you do your experiment. Then you're going to add, in this case, we are looking for the concentration of an acid. So we're going to add here the solution that we don't know. So in here is our acid, and we don't know its concentration. It could also be a base that you don't know its concentration, but this particular example, it's an acid. And you have to measure very precisely the volume that you're putting it in. So you have to make a very precise measurement of that volume. So you could use a pipette that only measures 20 milliliters, and that would be very precise. Or if you're using a graduated cylinder, make sure you use you measure it correctly. Then you're going to add an indicator. Okay, depending on what you're titrating, you need to pick an indicator that has the proper pH. So it depends on if you're titrating strong acids, weak acids, strong bases, or weak bases. And the indicator in this case that they're using is phenolphthalein. The indicator is clear when it's in an acid solution, and it'll turn pink when it becomes basic. Then you're going to use what's called a burette, and you're going to fill the burette. Well, first you need to wash the burette and then fill it and then try to get rid of the air bubbles. And if you watch this Carolina video here, it goes into detail on how you have to do that. And whenever you do a titration experiment, the first run that you do is like a rough titration, and you don't really count that as your data. That's just to give you an idea of where your indicator is going to change colors. So you fill this with your sodium hydroxide, and the sodium hydroxide in this case, you know the concentration. And then this here will measure the volume that you use. So you're going to add it in dropwise and swirl it as you're adding it. And then once the solution turns a very pale pink, you've reached what's called the equivalence point. And we'll go over these definitions of these words on the next slide. And then if it turns a very dark pink, then you've gone past the equivalent point and you're at the end point. And now your solution is actually basic. So here is a little schematic of what I just explained of how you do titration. You have a volume of a standard solution. The standard solution, you know the concentration. Okay. And then you could use the calculations that we did earlier with the balanced equation and the mole ratios and all that stuff. And you could figure out the concentration of your unknown. So a couple terms that you need to know is one, standard solution. This is the solution that you know the concentration. And this goes in the burette. The equivalence point is when you have neutralized your reaction. So if you're reacting HCl plus NOH to make water and sodium chloride, it's when you have equal moles. Because the mole ratio is 1 to 1 here, your equivalence point is when your moles of HCl equals your mole of NaOH. Now, if you have a different acid and a different base where your mole ratio is not 1 to 1, then your moles will just equal the mole ratio. The end point is when you get a color change in your solution. Now, in order to make sure your data is very precise and accurate, you want your endpoint to be close to your equivalence point, because you know to stop titrating when you've reached the endpoint. So you want these two to be as close to each other as possible so that the volume that you use to get to the endpoint is actually the same volume that you would need for an equivalence point. If you've gone too far, you've over-titrated it and it will affect your results. So here is a zoom up. So in the beginning, you just had your acid, you added your indicator. Then as you're adding your base, you're going to see it turn a pale pink. When it becomes this pale pink for about 30 seconds, then you've reached the equivalence point. If you've kind of missed it, which believe me, it is very easy to go right past it. That's why you do a rough run at the beginning to kind of get an idea of the volume that you might need to get it there. And then say you did a quick titration and you realized you needed 20 milliliters of the base. So then what you would do is add redo the experiment, add about 15 milliliters of the base, and then for the last 5 millimeters, you add it 1 drop at a time, so you can really see when it turns to pale pink. If you get to this dark pink, you over titrated. Okay, now your solution is basic, which means it's no longer neutral. You've exceeded the equivalence point. So let's do some practice problems here. So in this problem, which if you look in your book, it's in your book, one commercial method for peeling potatoes is to soak them in sodium hydroxide solution and then spray off the peels. The solution must be analyzed using titration periodically. In one analysis, you notice that 45.7 milliliters of your 1 molar acid was used to titrate 20.0 milliliters of your base. What is the concentration of the base? So the first thing we need to do is use our volume and our molarity of our acid to figure out how many moles. But actually, the really first thing we need to do is write and balance the equation. So we have HCl plus NaOH, and both of these are aqueous. Here's water, which is a liquid, and sodium chloride, which is also aqueous. So now we're going to take so what do we know? We know we have 45.7 milliliters of 1 molar HCl. So let's use this information to calculate the amount of moles of HCl. So let's start with our molarity. Remember, molar is just moles over liters. And since our volume is in milliliters, we need to convert to milliliters. And then we multiply by our volume. And that'll give us our moles. We need 3 significant figures because our given was in 3 significant figures. This is moles of HCl. Now we take our moles of HCl and we use our mole ratio, so it's 1 to 1 in this case from our balanced equation. So now we have moles of let me just erase that equal sign. Make it an equal sign. So now we have moles of NaOH. And they give us the volume of NaOH, right? So remember, molarity is moles of your solute over liters of your solution. So I have my moles, and I need to convert 20 milliliters to liters. Which just gives me 0.0200 liters. And then my answer is 2.29 molar NaOH. Okay, so that's using titration data and stoichiometry. So here's another example where we're using titration, and this is actually a process that they use to calculate how much chlorine is in water. So the quantity of chlorine ions in a water supply is determined by titration with silver ions. The endpoint of the titration is determined by a special type of indicator. The net ionic equation is as follows. So notice that the mole ratios here are 1 to 1. How many grams of chlorine ions, so grams of chlorine ions, are in a sample of water if 20.2 milliliters of 0.100 molar silver ion solution is needed to titrate it. So let's look at what we're given. So that's how many moles per liter of silver that we have. And if we multiply by our volume, so I'm just going to convert this milliliters to liters. You could write the steps like I did in the previous problem. But if you want to just save some time, you can take this number and divide it by 1,000. And you'll get liters. So when you do that, you get so you need that many moles of silver ions. But what is it asking for? Grams of chlorine. So let's take our moles of silver ions and use our mole ratio from the balanced equation. And it's 1 to 1. But it wants grams. So what we do now is in 1 mole chlorine ions, we use the molar mass of chlorine, which when you look on the periodic table is 35.45 grams. And then you punch it all in your calculator. And that is your grams of chlorine ions. Double check that your units cancel out using dimensional analysis. So in summary, mole ratios are important not only in stoichiometry, but using molarity and solution calculations. All right, when you're using stoichiometry, you're going to make sure you use dimensional analysis to make sure you're setting it up properly, or you could use the shortcut equation that we went over. Titration is the experimental process that is used to determine the concentrations of an unknown. And some key terms that we discussed was your standard solution, your equivalence point, and your endpoint. If you have any questions, let me know.